Hey everyone, welcome back, and today let's solve Leetcode problem 2406 titled Divide Intervals into Minimum Number of Groups. So we're given a 2D integer array intervals where intervals at I or index I is equal to an array of length 2 with left at I and right at I. Then these left and right endpoints in this interval represent the inclusive interval of left and right at I. And what inclusive interval really means is basically values of this inclusive interval, including the endpoints, right? Inclusive of the endpoints left and right for each interval in the input array intervals. So we have to divide the intervals into one or more groups such that each interval is in exactly one group and no two intervals that are in the same group intersect each other. We have to return the minimum number of groups we need to make. And we know that two intervals intersect if there is at least one common number between them. For example, the intervals 1, 5 and 5, 8 intersect. And you could argue, wait, this ends the exact moment that this starts, so technically they wouldn't be intersecting, but we know since they are inclusive intervals, 5 is present in both of these intervals because 5 is the endpoint or the right point of interval 1, 5, which is included because it's inclusive in the first interval, and 5, 8 is the left point, which also is included in 5, 8, and since 5 is a common element between these two intervals, they are considered to be overlapping or intersecting, and so we'd have to put them in separate groups. So as you can see, in example 1, we have the input array intervals to be a 2D integer array of 5, 10, 6, 8, 1, 5, 2, 3, 1, 10. And we'd output 3 because we know we can divide the intervals into at least 3 groups. In group 1, we can put intervals 1, 5, and 6, 8 because we know that they are part of our input array intervals and they aren't overlapping. And in group 2, we can put intervals 2, 3, and 5, 10 because, again, they are not overlapping. And in group 3, we have to put 1, 10 by itself because it overlaps or intersects with every single other interval. So it can be proven that it is not possible to divide the intervals into fewer than 3 groups. Of course, we can divide them into more than 3 groups, right? We can divide them into 5 groups because there are actually 5 intervals in this input array intervals, but of course that would not be as optimized as we can get it to be. So in example 2, we have the input array intervals to be 1, 3, 5, 6, 8, 10, and 11, 13. And we would output 1 because none of the intervals actually overlap, so we can actually put them all into one group. So for the constraints, we know that the length of the intervals array is not going to be exceeding 10 to the power of 5, and we know that every single interval in the input array intervals is going to have a length of 2, which basically tells us that we don't have to account or worry about any weird edge cases in our code. So with that problem statement out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem. Okay, I just realized I've been talking a little bit too fast. I'll try to slow down how fast I talk in the next few minutes of this coding. Okay, so to solve this problem efficiently, we have to actually use a greedy approach with a minimum heap to solve this efficiently. And so first we're going to actually approach this problem by sorting the intervals based on their start times, and then we'll use a minimum heap, or also known as a priority queue, to keep track of the earliest end times of meetings currently in progress. And for each new meeting, we'll check if it can fit into an existing group by comparing its start time with the earliest ending meeting in our heap. And so, like I said before, we'll sort the intervals, use a min heap, and add to the heap or reuse a group, essentially saying that for each meeting, if its start time is after the earliest end time in the heap, it can fit into that group. So we'll remove that group from the heap or pop from the heap and basically indicate that it is a non-overlapping group. And otherwise, it requires a new group, so we'll add it to the end time of the heap. And the result size or length of the heap at the end is going to tell us how many groups are needed to optimally split these intervals into at least or the minimum number of groups needed. Okay, so we really have an optional line of code. I could import the heap queue module and just to better show how these data structures are stored and which modules and or dependencies are needed to actually get all of these different data structures in Python. I'm going to just import heap queue. Okay. And again, this basically imports Python's heap queue module, and that's because we're going to use this module to create a min heap, which is going to help us manage the time or the meeting end times efficiently. And a min heap always keeps the smallest element at the top, so it's perfect for tracking the earliest end time. That's why it's called a min heap. Okay, so now we're actually going to solve, or rather sort, the intervals input array by its starting times, and in Python it's especially very easy to do that with lambda functions. Now I know lambda functions are also in C++ and statically typed languages like that, but they are a little bit harder than it is in Python, and you guys will see why in a few seconds. So we'll literally just hit the intervals.sort method that's built into Python, and instead of just sorting regularly into ascending order, we'll pass in a key for this sorting method and set it equal to an anonymous lambda function with a parameter x, and sorting it by x at index 0, the starting time. Okay? And sorting basically helps us process the intervals in chronological order, ensuring that we handle earlier meetings before later ones. Now we'll actually initialize that min heap data structure, so I'm going to literally call it min heap, and this is going to be initialized to a minimum heap. And basically, we're going to use this to simulate a min heap where we'll store the end times of the current active meetings, and the heap helps us keep track of the smallest end time, basically the meeting that finishes the earliest. So now let's actually loop through the intervals array. So I'm going to say for start and end using two iterators or a pair of iterators in Python, because we know that every single interval is going to have a length of 2. So for start and end in the intervals, and actually this might seem a little bit counterintuitive, so I'm going to say for left and right, just so it's a little bit easier to understand what they actually signify. So for left and right in the intervals input array, again, this loop basically iterates through over every single meeting interval on the sorted list, and we're basically unpacking each interval into two variables. We'll have the start, basically the start time of the meeting, and the end, or the end time of the meeting. So now, in every single iteration, as we traverse through the input array times, or intervals rather, if the min heap is non-null, just so we don't have a list index out of range, and the min heap at the most recent, actually I'll just say 0, it doesn't really matter, at the most recent end time that we've added in the previous iteration, if that's actually less than the start. And again, this basically checks whether the heap is non-empty and whether the earliest ending meeting, min heap at 0 or -1, ends before the current meeting's starting time. And if so, this means the current meeting can fit into the same group as the meeting, as their times don't actually overlap. And so we can hence heap q.heap pop from our min heap. Okay? And basically we're removing the earliest end time from the heap using this heap q.heap pop operator, and this frees up that group for the current meeting since its earliest meeting has finished before the current one starts. And outside of this if statement, for every single for loop or iteration of our input array intervals, we have to heap q.heap push onto our min heap the end time of every single interval, right? And that's basically going to ensure that the heap keeps track of the ending time of this meeting, which may affect future meetings in future iterations of our input array intervals. And ultimately, we just have to return the length of the intervals, or the min heap, because that is going to eventually tell us the number of groups required to hold all the meetings without overlap. And each element in the heap represents an active group of meetings. Okay? So before I actually submit this, kind of just an overall explanation of what this code actually does. I'll go as slow as possible again. Okay, so the code basically works by iterating over the sorted intervals based on each interval at its starting time and managing the meeting groups with a minimum heap or a priority queue. And this heap is going to keep track of the end times of the ongoing meetings, and for each meeting, we'll check if it can fit into an existing group by comparing its start time with the earliest end time. And if it can, we reuse that group, and otherwise, we'll create a new group by adding its end time to the heap and comparing that for future iterations. And so at the end, the number of groups required is simply the number of elements left in the heap, as each element represents an ongoing group of meetings. So if I were to submit this code right now, unless I spelled something wrong or made some syntax errors here, this should be accepted. Okay, let's see here. Yeah, so this should be in fact, I'm just going to use start and end just to better simplify this. But note that start is basically representing left and end is representing right. But now, as you can see, this is just about as efficient as you can get. Really, it's beating nearly 100% of users, and you really can't beat how fast this code is, right? So for the time complexity of this program, since we know that sorting the intervals actually takes a big O of n log n operation, where again, n is the number of intervals, we know that each insertion and removal from the heap takes big O of log k, where k is the size of the heap. And so in the worst case, the heap could contain all n intervals, and so the time, therefore, would be a runtime complexity of big O of n log n due to the sorting step being dominant, right? Big O of n log n being strictly slower than big O of log k. And for the space complexity here, this is going to be big O of n, or linear time, because in the worst case, all intervals could be active at the same time, requiring us to store all of their n times in the heap at once. Okay, so if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I'll see you guys in the next video. Bye-bye.